Righto, this is a worked example for quite an interesting problem in the coordinate systems topic within the Edexcel further maths syllabus. And it's basically coordinate systems. It's basically coordinate geometry. If you're doing A-level maths or have done A-level maths, then basically it's kind of a hard version of the problems that you get in coordinate geometry. But as we go over here, uh, essentially we've got more complex curves. In this case it's a parabola, but we've got hyperbolas, ellipses, and so on. Um, the the problem is quite difficult in the sense that we've got a combination of parametric and Cartesian equations all kind of rolled into the same problem. Um, at A level, there's much more distinct as to whether or not you're working with your parameter or with your Cartesian variables. And then we've got other unknown parameters, A, C, in A in this particular one, which are unknowns, which add to the complexity. But at the end of the day, I mean, we're using all the same toolbox that we tend to do with our coordinate geometry problems. We've got gradients of tangents, using calculus to find the gradients of tangents. We've got gradients of perpendiculars. Of course, the perpendicular, you multiply the gradient by the gradient of the perpendicular, get -1. Equations of intersection, where we're sort of eliminating one of the variables and get an equation, very often quadratic in x squared, but maybe other things. We're using lengths and distances, we're using midpoints, all those kind of toolkit things that come with coordinate geometry. They're all part of this problem as well. So let's have a look at the problem then. The parabola C has equation y squared equals 4ax, where a is positive constant. The point P AT squared 2AT lies on C. So the AT squared and 2AT are actually therefore the parametric version of the curve. Um, but it's given to us, if you like, in this particular form. Using calculus, show that the normal to C at P has equation this. Right, okay. All right, so I've kind of done a sketch on it here, a sketch aided by Desmos. Um, there's some stuff on here which pertains to later sections, but we can just imagine the red curve there. So that is more or less where we've gone. I've used a parameter of a equals 1, just so that to kind of give it some scale, just for illustration purposes. Um, okay, so we've got to show that this is the equation. So let's just have a look. We've brought it down here using calculus. Show that the normal to C at P, there we go, has equation this. All right, so typically with these things, we're going to find the gradient at the general point. So if we differentiate with respect to y with respect to t and x with respect to t, we're going to get this. Dy dx equals dy dt times dt dx, and that's using the chain rule to sort of unwrap this derivative here in terms of the parameter t, and that's going to give us a gradient of the curve of 1 over t. So the gradient of the normal to the curve is going to be that such that, of course, these two things, when multiplied together, give you -1. Uh, And then if we then apply the general point together with our known gradient and use this particular formula for finding the equation, then we can plug our y in there and our x in there together with our gradient, work that through, and that's going to give us that. So that is part A. So I've shown that. Right. It goes on to say the point S is the focus of the parabola C. B lies on the positive x-axis and OB equals 5OS, where O is the origin. Write down in terms of A the coordinates of the point B. So that's a relatively straightforward one, because we're given that the curve is y squared. That should be y squared is equal to 4ax, and the focus is there. So sorry, so the um, so the basically the focus is at A0, so that's S, and OB is twice as long, so OB must be 5 times OS, and therefore B is the point 5A0. Okay, so that's not too bad. Obviously, that part you do need to know about parabolas and those kind of relationships. Right, now this is kind of the main tricky bit, I think. I've replicated this diagram down here just to kind of make it easy, because I can't get everything on the same screen. Circle has center B and touches the parabola C at two distinct points Q and R. So that's what we've got. We've got this circle here, and we've got the Q and R here and here. Okay, find the coordinates of the point Q and R, right? Okay, so the trick here basically is, if you can imagine the normal as t varies, the normal is coming around here like this. Yeah, down there it's going to be perpendicular to the tangent, isn't it? When it gets to this point Q, then this normal will actually pass through this point, which we have just calculated, 5A0. So we could just use small t, but I've actually found this clearer if to kind of to sort of say, well, look, there is a specific value of t. T is usually a time parameter, isn't it? So specific point in time, you might say, big T. And at that point, the normal to the parabola passes through this point, 5A0. Okay, so and at that point there, the coordinates of this point here, done by instantiating t, t is the exact value. So this is the coordinates for this point Q. Right, so the equation of the normal is this. What's the equation of this thin black line coming down here? So when t equals t, the equation of that normal is going to be, okay, we're going to use this. This is from part A. Substituting t, we're going to get that. And we can also take account of this fact. So we substitute x and y into there and there, and we get this equation. It's an equation in t, obviously. So, and when we solve that, that's going to give us these values of t, plus and minus √3. Okay, just follow that through if you like. That's just a simplification. A drops out, interestingly. Okay, so therefore that gives us what P is, because we got our values of t that we can substitute in there. So P at the points where it touches the circle are going to be what we get when we realize this, and that's going to be 3a and 2 times the square root of 3 times a and the negative of that. So that's what these 2 points are here, Q and R. Okay, perhaps write Q and R on there, which is a be clearer. Okay, so all right, so that is what we've got there. So now that is not altogether straightforward, is it? And it does depend on actually spotting the fact that the normal this normal will pass through a point that we know, and that's what enables us to kind of solve for that. All right, so that's part C. And then finally part D, sort of relatively straightforward, I think, is hence find in terms of A the area of triangle BQR. Well, of course, what we've got is we've got this triangle here. And we know this distance now. So we know the two y coordinates. And we know this perpendicular distance here, which is given as is basically the difference between the 3a here and the 5a there. So that's 2a. So the area is just going to simply work out as the half base times height. If this is the base and that's the height, then that's going to give us 4 root 3a squared for the area of that triangle. Okay, so yeah, it's a bit of a tricky problem, but most of it, to be honest, is just kind of plodding through calculations. I think the two difficult things in this one in particular are the fact that we've got the parameter t and the x and y's kind of mixed up, and so that takes a little bit of unpicking. The other thing is spotting this trick that the normal will go through this point B for which we know the coordinates. So anyway, that's it. I hope you find that useful, and I'll see you in the next video.